So I'm just gonna run through this like it'll be a pretty quick session. Um, I kind of just like went the high level routes because a lot of the implementations kind of already exist. For Paxos, I'll just kind of like cover where it's used. And I'll kind of just explain how consensus kind of exists in databases, since it's more like database internals, and kind of cover like some of the algorithms to kind of list in the book. Um, so yeah, let's kind of kick it off. So my name is Batman, or Emmanuel Bakare, but everyone calls me Batman. Um, I'm senior DevOps at Twilio. I'm mostly on Twitter where I should post most of the time. And my GitHub has some interesting projects that you might like. So yeah, that's mostly about me. I'll dive straight in. So it's basically going to cover like these things, just like the definition of consensus. Consensus is usually just aligning on distributed transactions. So if you think about it that way, you're kind of on your way, right? It's mostly like all of that. The different consensus algorithms mostly work for scalability, fault tolerance, better performance. And some of them handle cases where it is difficult to arrive at consensus. Say you have multi-leader assignments where two people are writing into the log table and you need to consolidate all of that. You know, a lot of us might not, I think, of multi-leader like, oh, something else, but it's pretty much like when you're editing on Google Docs, that's a very simple example of a multi-leader kind of, transaction, because everybody's, because some people are writing, some people are just looking at the document, but you all kind of need to align on who's making changes to what. All of those are CRDTs. I just thought to just mention that part. Like consensus isn't like a really big buzzword. Sometimes it's just as simple as what you've already been used to day. And yeah, and some of the challenges pretty much. Um, I kind of went the route of covering what's in the book, but tailoring it mostly to what I understand the database. So we'll kind of start off from here. We'll go through two-phase commit and three-phase commit because I was of the opinion that it wouldn't really make sense to go through what do you call it, consensus without really mentioning how these are even applied generally. And it's kind of like the most important bit to understanding Paxos and Raft. Um, so yeah, I mostly just like start off with two-phase commits. Usually this is quite simple. You have a prepare and a commit phase. Most of us who have written um, SQL queries where you prepare a multi-level what do you call it, SQL query that you have select, inserts on like multiple lines. Those are multi-level queries. And usually the database um it doesn't just like commit each one like in a single go. It prepares the commits, checks if they are all correct, and then it applies them. And if one of those commit fails, it aborts, right? Which you can see here. It basically aborts it. If everything agrees, then it commits the transaction. Usually two-phase commits are like they're applicable because they're atomic and it's very simple to implement, right? So usually this is kind of what I mean, in SQL context. And yeah, this is kind of pivotal to understanding when we get down to ZooKeeper and Paxos, you kind of see where two-phase commits kind of come in. It's like the base level for all these things. But yeah, this is kind of it. Usually when you make a transaction, you prepare, you insert. This could be anything. This insert could be like Google Doc example. You type it into the sheet. This could be something actually publishing an event into a queue, or various other things like that. This could be the right event on the database, and that being propagated to multiple replicas, that kind of thing. So all those kind of things are kind of how two-phase commits come into play. And it only works if everything can agree, right? But as you then imagine, this can be tricky because when you have multiple distributed systems, for those of us who remember the session on that was on the FOP impossibility, you can't really have a system where every single system is consistent, kind of relating to the what do you call it, to the triangle. So yeah, it's kind of just like that. Two-phase commits are really good where you have systems that can handle atomic failures, where if one system fails, everyone kind of fails, with negligible latency, that they all kind of, continue processing other transactions, and enforce that serial consistency model. Yeah, so that's two-phase commits. To kind of work around that issue where multiple nodes can fail, and you kind of need to like reconcile that agreement process. That's where three-phase commits kind of come in. So in three-phase commits, what happens is that the you now have a pre-commit phase, then it commits before you actually run the transaction. So the reason for this is that when you have multiple nodes, with the two-phase commit, you prepare and then you commit. But if one node fails, it becomes quite hard to roll back, right? Because then you have to send another event to commit, and then you just repeat the two-phase commit process of preparing the transaction, sending it out to the replicas to commit the rollback. But if they fail, you kind of get this inconsistent state. So the idea right now is that the leader keeps track whether all the replicas can commit in the pre-commit phase, and then if they all can, then they commit. We are already aware that the commit is successful. So usually this has a much nicer failure rate, because in the pre-commit phase, we already know if that transaction can succeed on it. And usually this is, as Haley was discussing earlier, a form of broadcast, which is kind of discussed in the book, where you kind of have like this model where transactions are kind of sent out, right? And then each node is trying to course correct, on that particular transaction. Usually this is, I guess, what would I even call it? A peer-to-peer broadcast. It's not really like gossip, where like, you have cross-chain, what do you call it? Cross-chain, transactions where a replica can, gossip to another replica. This is more just, peer-to-peer, leader to replica, leader to replica. And if they can all pre-commit those transactions, then, we prepare the transaction and then we commit it on each of those nodes. So that's kind of how three-phase commits work. Usually when you dive into the implementation of Raft and others, they all kind of blend in three-phase commits, because that's kind of how it works. When you think of like blockchains are a very good example of consensus in the wild. You have like multiple nodes trying to validate the transaction. You have the 2/3 or 50% requirements, depending on what version of Paxos you are implementing, whether it's fast Paxos, multi-Paxos, etc. So three-phase commits are kind of like, what all the others kind of borrow from. Raft is a different instance of that, but when we get there, I'll kind of explain. So this kind of a diagram kind of illustrating three-phase commits. So everybody kind of coordinates. Usually the coordinator and participants. Coordinator will be the leader, right? In this case, the master node kind of sending out all the transactions to all the participants, noting whether they can actually perform the transaction. That is to commit the transaction, and end the entire process, of consensus. So the leader sends out all the events. They all vote whether they can do it or not. They prepare to commit. If they can prepare, then the commit is done. And we all kind of just move about our day. But the beautiful part about three-phase commits is that when the prepare fails, everything fails. So we don't really have to, bother here with rolling back the transaction or arriving at inconsistent states. A lot of this was covered by the Finch-Lynch impossibility paper. So I need not dive too deep into the theory of, what backs this kind of, process. So yeah, like I said, three-phase commits has this advantages: reduce blocking, enhanced fault tolerance, and flexible timeouts. They require more transactions, so usually you kind of have this bandwidth issue where you have multiple same transactions, which is kind of where Paxos, broadcast, gossip, etc. kind of come in, because you reduce that n by m um, transaction flow, and that kind of helps with the issue with the broadcast model that we face implements. So usually broadcasting consensus, as I've been discussing, there's quite a lot of things that I've said, mostly just saying broadcast a lot. But consensus algorithms require some broadcast mechanism. Usually broadcast is just a big word for how can I send this message to all the nodes? And it runs all the way from networking, where you have like multicast, or unicast, where you kind of have one-to-one pairing, or multicast where you have one-to-many pairing. And it's basically just a way to send out the message. Like when you send out a tweet on Twitter, that's a broadcast one, right? Because you send a tweet and that tweet is disseminated to millions of devices, right? What do you call it? There's usually some filter, but it's still a form of broadcast, right? And gossip, right? Gossip is a very simple way to think of gossip is torrents, right? Because torrents, the way torrents work is that you have a peer, right? And then you are basically a leech, right? Which is a seed leecher, And the idea is that the leechers are the guys pulling from the network, the seeders are the guys that, provide what the leechers take. The thing about torrents is that as you are leeching, you're also a seeder, right? So that means that as you download a particular block of the file off the network, you can also send that block to someone that needs it. Right? And that's a very beautiful example of gossip without the complicated examples. You seed, you send the file to somebody, someone can send the file to someone else. And that's why torrents are so difficult to take down, because there's no one single master, right? Everybody is a master and a slave, right? Coordinating those transactions across each other in a very well-distributed network. And gossip, just like the 3PC model, it's very simple because there's no coordination between the seeders and the leechers. Everybody is just, oh, I'll pick this guy from the list, right? Oh, there's just like a central list of all the seeders and leechers on the network. And then, you just pick a random person, check if they have the file, they send it to you. That's kind of how it works. So gossip is beautiful. Another example of where gossip is found is in a Hedera hash graph. So for most of us who might be into blockchain, a Hedera hash graph, it actually has a gossip model for how it actually transacts. They call it gossip on gossip. And when it came out, it was actually quite, I guess it was quite a revolutionary model for that kind of transaction flow using DAGs. Usually all blockchains are DAGs, micro trees to be more precise. But you kind of get the idea of like how gossip works. It's basically just sent to one person and that person now holds the information. They can send it to someone else, without the actual person that sent it to coordinating those transactions. They basically become independent once that transaction is completed. And in consensus, this gossip-based model is effective for message propagation, but not for actually reconciling consensus. Usually that would be managed by a different party in the network. They usually call it a notary, right? So the notary just trades like notes of, all the nodes in the network. And it's like, do you agree? Do you not agree? But the message flow is independent of the notary. So it usually avoids broadcasting issues where the actual notary just can't manage, millions of nodes. So it scales well. Sending those messages to millions, timeout, all those things. Flooding broadcast, where what do you call it? So this one is kind of like a very good example I can use to explain flooding broadcasts is Raft. So Raft actually uses where is it? Raft GitHub bio. Where is it? Here. So Raft is based off Paxos, but it's kind of uses a so let me just wait now. So like when you see this, it's kind of like this is how flooding is kind of like. But just imagine if this sends to here, then this sends to everyone else, right? So that's kind of like how flooding broadcast is like. Here is just a one-to-one kind of flow, right? S1 sends to all these 4 nodes, right? And they all kind of send the message back. In flooding, S1 sends to S5 and then S5 sends to all of them. So it's basically an N-squared broadcast model. Usually it's very difficult, right? Because it overwhelms the network, because now rather than having a N chain network where, each node sends to one node and then that node can send to another node that has not received the message, that Cedar Licha model, it's now basically N squared rather than N in the case of gossip. So flooding broadcasts tend to be very inefficient. You'd mostly find flooding broadcasts in I think like the Bitcoin network, I think is a flooding broadcast. I can't remember, but flooding broadcasts are generally inefficient, so people don't really kind of use those. I can't remember. I remember kids where they were using flooding broadcasts. I can't remember again. Optimized broadcasts usually you're only targeting the relevant node. So this kind of like the filtering I was talking about with the tweets, where you send a tweet on your phone, the tweet goes out to multiple devices, but it's only for those devices that follow your tweet feed, right? So that broadcast is kind of siloed. If you are not following me, you won't get it. If you are, you get it. And then the Twitter network, in its own model, has a For You page or random feed where any random set of tweets can just go to any random person. Those tweets could be prioritized based on if they're paid, if they're ads. That's kind of like where you find optimized broadcasts models and all of that. So usually in Consesus you would always have broadcasts because you need a way to disseminate information to all the nodes or some of nodes in the network. The book also talks about something called virtual synchrony. So usually in databases, the way that we would kind of define this is using serial consistency, right? So serial consistency is kind of like the thing where even if messages are out of order, they can still be processed in order. And virtual synchrony is kind of like a build on that, where you kind of have consistent message ordering, fault tolerance, reliable delivery, all the buzzwords, but usually it's still focused on the exact same thing that, like, if you leave the network, you join the network, you still get messages delivered to you in the same order that they were sent, right? And yeah, it's basically just like the building block for all the consensus processes that we described. How this is managed, it differs a lot. Like for example, in Kafka, the way that this would work is that you would have groups. So what that means is that nodes are groups. So basically someone in one group can read all the messages, but when someone comes online, they would see all those messages delivered to them in the order they were sent. A very good example of this would be like WhatsApp, where even if you are not present on the network and you're offline, the messages are kind of held and they're delivered to you when you do come online, so that, you're kind of like up to the last feed. That's kind of like a very good example to explain virtual synchrony, but not in the consensus model. But you can kind of see, like, once you receive those messages, you can then transact on the network. because you have all the information provided to you in the order that it was initially sent. That's kind of like how I would explain virtual synchrony based on what the book describes. So yeah, it also talks about ZooKeeper atomic broadcast. Yeah, so it's kind of like all nodes is basically the exact same build on virtual synchrony, just for ZooKeeper. For those who might not know what ZooKeeper is a distributed, I don't know how to explain it, but it's basically built on top of Kafka. It's the manager for the nodes and all the transactions that are propagated across the nodes. So you could call it, I wouldn't call it distributed transaction manager. Let me actually check out the right terminology. Yeah, it's basically a central distributed configuration, or yeah, distributed coordination manager. Like that would be a way to describe it. So ZooKeeper is like what you use to manage, say, keeping track of how many servers are in pool, keeping track of how many servers are transacting on the pool, the last time transacted, last committed time, all those other kind of things are what I'd say ZooKeeper manages. Okay. I thought someone raised the question. And yeah, so that's kind of where ZooKeeper kind of comes in. And the atomic guarantees is just based on the concept of virtual synchrony, where if you send a message, you're going to receive your message so that was sent. And that, what do you call it, coordination model stays in place and consensus is always achieved. Usually all the big buzzwords, basically ZooKeeper is, labeled that discovery, everything else is kind of like the same thing. That's kind of how I put it. And yeah, so we've kind of come past all of that. I'd pause here for questions. Does anyone have an idea? And I have any questions before I continue? Anyone? Okay, cool. So the next thing we're going to be talking about is Paxos. So Paxos was developed by Leslie Lamport in the 1980s, and Paxos is a distributed consensus algorithm, basically one of the most widely used. Paxos is reasonably quite complex, and it allows you to have multi-leader transactions. And multi-leader transactions are incredibly difficult to negotiate in a network, and particularly in consensus. So usually, as I've initially stated, usually find Paxos in blockchain networks because they are usually the networks that have multi-leader configurations where multiple nodes in the network can transact. In fact, based on blockchain ideals, like all the nodes in the network can transact, right? And that virtual synchrony still holds, consistent ordering of events in the network and arriving at consensus, all of that still holds. Usually when you are considering basic Paxos, you're usually of the idea that, n+1 nodes to be in agreement with 2n+1. Usually that's just a 50% agreement. You can also likewise achieve this with something called the law of large numbers, where like if you take the average, I can't remember how to do that here on Wolfram. But the general idea is that it's usually just like, well, you could also do this using, like, what do you call it? I've forgotten the term. Calculus. I've forgotten. But technically, like, you can just do D over the N or the top and the bottom, and you can kind of arrive at, what that percentage model should be, 1/2. If it's 2n+1, where you assume that n nodes are defunct, you have 2n+1, then 3n+1. That's usually the fast Paxos tolerance model, etc, etc. That's the way that the consensus requirement is guaranteed, that this number of nodes against this total number of nodes in the network need to agree that those messages are correct. And usually it uses a two-phase commits model. Paxos has three main components. There's usually the proposer. So the proposer usually will select the proposal number and send that proposal number to the acceptors. This is the ordering is basically based on Lamport's clock, which is not particularly surprising since there's a Lamport in the algorithm. So Lamport's clock basically is an ordering, rather is a monotonic counter that basically gets the value of time based on the number of events sent. So if you sent 5 messages and then you sent a 6th one, the time of the event is basically 6, right? And it doesn't matter whether that 6th event came 1 day or 1 hour after the 5th event. So it's kind of really good because if you're transacting across different time zones, you're not particularly bothered with clock skew and various other problems that kind of come with, ensuring consensus and ordering events in a widely distributed system that could, span regional or global, servers, that kind of thing. So that's just like, I'm just, raising another like extra point here about like, the prepare phase. In the promise phase, the acceptors, they accept the prepare message, the proposal, greater than what it has seen before. So that's kind of how you know whether, a counter, I don't know what to call it, like counter transaction was put on the network, and the acceptors will take that to be like, okay, if someone proposed 5 before and another node on the network proposed 6, then we are going to basically take event 6 because it's higher than 5. But you won't but after taking 6, you're not going to downgrade to 5 because, there's a difference in the ordering of the events. And that's kind of like how Lamport's clock, in addition to Paxos, ensures that consensus across all the nodes is achieved, provided those nodes can receive the transaction for that event through that event on the network. And then basically once each of them has basically accepted that transaction across the network, it basically then runs a tallying of how many nodes have 5, how many nodes have 6. If more nodes have 6, then the transaction is completed, and we basically accept that all the nodes agree on 6 being the value that we want to agree on in the network. That's a very, very simplified version of how Paxos arrives at consensus, right? And through all of this, there's usually broadcasts, across the network, back and forth. And yeah, everyone is kind of tallying up what the nodes in the network have agreed on and bringing that back. So this is useful, in things like distributed locking, where you're trying to agree on who owns the lock, like that 5 and 6 model. If 5 was previously owning the lock, and say like it was a lease, and then 5 what do you call it, lease time ran out, and 6 is the one that's supposed to have it. Even the node that proposed 5 to own the lock, because that timing is kind of off, and the lease has expired, 6 is now the one that is proposing that it own the lock, and all the nodes agree that 6 should own the lock, 5 will basically be left out. Same with data election, state machine replication, all those other kind of things are what is there. But because Paxos has this n by n model for transacting events, because all the nodes have, or basically a percentage of the nodes have to agree, whether it's 66% or 50% or some other weird value, depending on what variant of Paxos you run, it's basically arrives at slow convergence, right? And usually you would find this kind of slow convergence in networking 2, where you have what do you call it, routes, what do you call it, like BGP, for example, and advertising routes, etc, like which route do we accept, which route do we accept. That slow convergence model is found whenever you use Paxos, which is what Raft kind of solves. The benefit of Raft is that you have a single leader and then you have multiple replicas. So in places like databases where you don't really need multiple masters, Paxos is great when you need multiple masters. And basically, based on the book, that's how you can understand when to either use Paxos or Raft or find another distributed consensus algorithm. Paxos is for multi-master. You can think of it that way. Anytime you need multi-master, just go straight for Paxos. If you need a single master, Raft is usually best. It's more performant, what do you call it? And it assumes that the nodes on the network will fail, right? Paxos kind of has this low convergence and it assumes that majority of the networks are available, right? With the percentage thing, which is kind of where you have the Byzantine, what do you call it, general's problem, what do you call it? And Paxos kind of solves that with the different version of the algorithm. So etc. Raft is usually best for single master. And this is just kind of an example of just what I just explained. Client, proposer, and all the acceptors and the learners, usually they just kind of keep track of the state of the network and who owns what, etc. Yeah. So Raft. So in the book, you kind of went through Paxos. Quorum, I kind of already explained what quorum is. Quorum is basically all the nodes coming to an agreement. I've explained the failure scenarios. I didn't dive into the various types of Paxos because they all kind of borrow the same model. Like if you think about it, just with different quorum percentages, and then the approach arriving at quorum, which is kind of just where Paxos differs across the various, its implementation. So Raft was invented in 2013. And the benefit of Raft is that you can achieve consensus through a leader election process. So remember what I was saying about a single leader. So Raft basically brings in that, okay, we don't need multiple leaders in the network. In fact, we don't want all nodes to assume the role of leader and propose events on the network, that kind of thing. Rather, reconcile events on the network. So the idea with Raft was that we elect a single leader. Those leaders are elected by all the members in the network. They transact with the leader. The leader keeps track of the state of the network, and then the leader disseminates that information to all the available nodes on the network. So it's easier to implement because you only have to manage the log on a single instance. And when you think of the write-ahead log in databases, you can kind of liken it to Raft, especially when it's not a single database instance, it's multiple databases. That's how you can think about like leader election. Assigning one instance as the master, and then you also have replication lag, all those kind of details kind of built on the entire concept of Raft. Because it's always ensures that it's a single leader, the strong leadership guarantees, and safety in the event of failures. If you have a partition where in this case, like a partition is like here, like 4 and 3 are basically now the only ones transacting in the network. These two will continue doing their work. 4 and 3 will allocate a master between themselves. 5, 1, and 2 will allocate a master along themselves. They'll both transact on the network. But when the network reconciles, then all 5 of the nodes will then try to basically then pick up a single master because now they've discovered other nodes in the same network, and now they're trying to then reconcile what the master should be. An example that I can show here is that if I stop, not stop S1, like resume, why did it pull that here? Like if I stop S1, then I start it again. Yeah, so you can see that they're all timing out. S1 is stopped. You can see all the nodes. Yeah.
Sorry. Are you sharing like an image? Because all we see is like text.
Oh, damn, that is bad. Okay. Thank you very much for that note, because I did not know that that was actually not sharing. That is bad. Sorry about that. So yeah, so let me go back and then actually cover that. So this is Wolfram, this is Raft Visualizer. So the basic idea here is that let me start this again. It starts. So the way Raft works in comparison to Paxos, where Paxos kind of assumes you have a multi-master model and all nodes are transacting on the network. So you usually have this n by n events requirements, and that can be very tasking on the network. Because remember, even though you are seeing transactions, you are sending something to a server, right? And basically that server is then receiving for multiple nodes at a single time. So it can be very hard on whatever is coordinating that request. Could be the switch, in whatever data center you're running on. It could basically just also be just, whatever router is, managing that information flow, etc, etc. Right? Raft only assumes that there is one node leader that is basically taking note of all the events in the network. All these nodes transact only with the master. So you only have an n, what do you call it? Like you only need bandwidth for n transactions at any given time, unlike Paxos where you need like n by n, right? And the beautiful thing about Raft is that if one of the, like if the master does, for some reason jump out of the network, what happens is that all these nodes will, whoever, times out first, will basically then, what do you call it, try to renegotiate who the master is, and then basically assume that role, right? Since the master replicates the log to all the replicas, S4 theoretically should be up to date. And in assuming the role of the master, he basically just continues, increasing the transaction log for the master, so that when S2 comes back, S2 basically just replicates from S4, and then it also becomes a replica in the network. So if I were to then resume S2, you'll kind of see that S4 still stays as the master, and you can see that now this guy is, basically then transacting just as normal, but S4 is still master. So that's where Raft kind of supersedes Paxos, because it has that strong leader election. You can kind of assume that if the master fails, the network continues. So there's better partition tolerance. The reason for that is because Paxos assumes that n plus 1 out of 2n plus 1, or 2n plus 1 out of 3n plus 1. There's different consensus requirements for quorum in Paxos, depending on which implementation you pick. So Raft is also then much simpler, because you don't need to be doing all that math and assuming, oh, if I implement this model, what do I need? etc, etc. So it has all these things: leader election, log replication, consistency checks. I already kind of explained how that works, because it assumes that since it's the leader, it basically then, what do you call it? It assumes replication lag is minimal. So usually you can be sure that transactions across the network kind of all reach one single node, provided there's no partition. And even if there's a partition, that partition will pick its master, the lower partition will pick its master, and then when the network then aggregates again, all of them will then basically try to pick a master by, once the two masters, one of them is going to time out first, send the messages to all the replicas in the network, and then that leader will basically renounce his position as the master and then join the network as a replica. So that kind of consistency is, where Raft kind of falls in. And for most of the book, it just kind of like talks about this leader election that I just demonstrated. There's not really much in there that I think I would expand on. There is Yeah, that's pretty much most of it. Um, and Raft is basically just as simple as that. It's quite as efficient as you want it to be. Yeah, that's kind of it. For what the book kind of describes. There's the Byzantine fault tolerance problem. And all the Byzantine fault tolerance assumes or proposes is that basic Paxos has this number of nodes that are required. The assumption is that there are n number of nodes that are basically, what would I call it? You could call them Trojan horses, you could call them faulty nodes. You just assume that, n number of nodes in the network are basically defunct, right? And what that means is that this n plus 1 to be in agreement to n plus 1 becomes 2n plus 1 need to be in agreement with 3n plus 1 nodes. Usually, basic Paxos, if you think about it, this n plus 1 divided by 2n plus 1 is approximately 51%, right? This basically then takes it up to 66%, which is what you would see in 2/3 of the network need to be in agreement. That's basically what you find with blockchain networks that implements Byzantine, have some implementation of Byzantine Paxos. There's a lot of weird ways that consensus happens in blockchain. There's proof of work, proof of stake, that kind of assumes the Raft model in a way, blends both of them together. So I can't really describe it, but based on what that Byzantine fault tolerance assumes, that is all you need to kind of remember. It's basically like basic Paxos, but you assume there's another, n nodes that needs to also be in agreement, etc. So it has a stronger consistency requirements, which is what I basically explained here. 2n plus 1 out of 3n plus 1. And yeah, so like here, I'm just basically diving out of the book. Everything that's kind of explained here is what already exists. Although there were some things about pre-preparing, but we already kind of explained those prepare commits in three-phase commits, which is why I emphasized on three-phase commits, because a lot of all this Paxos basically just blends three-phase commits into its implementation. So if you understand three-phase commits, you kind of understand the prepares, the prepare, the commits, all those kind of things. It's basically just the same implementation. And yeah, so that's kind of all that I had planned for this session. Are there any questions? Because I know I've been talking a lot.
I think Brian, I think you had your hand raised earlier. Did you have like a question? I'm not sure where we were. I think we're in the middle of Raft.
Okay, let's hear. Yeah, I'll go for it.
No.
Yeah, sorry. I just wanted to mention the issue there with the screens.
Oh, okay. Yeah. That was my bad. What do you call it? I didn't know that wasn't sharing, which would have been strange. So it only shared the tab, not the window. So my bad there. Yeah, but I hope the later parts I did cover like some of the important bits. I hope that there wasn't anything that was missing in the explanation.
Yeah. So I think it made sense for me at least. So I just wanted to ask for Raft. Yeah. You said it can only have one leader, right? At any
Yes.
given point. So I'm not sure how like a multi-cluster would work. Say multi-cluster of 5 nodes each. So do they get like a single leader, or you have like a master node per cluster?
Multi-cluster as in Kubernetes, or multi-cluster just like in general?
Maybe let me
general.
clarify. Let me help
Yes,
clarify the
yeah.
question. It's more that, say you have like 5 nodes, like in this Raft example, how does the algorithm ensure that there is only one leader if the leader fails, right?
Oh, okay. Yes. So usually Raft will have timeouts where if it cannot communicate with the master, think like basically this is a lease, right? So it holds a lease. A lease is basically a lock with a timeout. So you can think of it like that. So basically he holds a lease with the master and he renews that lease within the lease's time period, right? If it cannot coordinate renewing that lease with the master, with the existing master, then it basically then tries to pick a new master. Now, usually sometimes, right? Because this is kind of simplified. If you think of the implementation, like practically, that's where kind of ZooKeeper comes in for coordination, where it's like separate from the actual network and the nodes that comprise the network, and ZooKeeper will manage that, assignment, right? If it kind of makes sense. Or you could use console, right? Console is also another what do you call it? Service that can kind of do it. And the idea for most of the implementations of this is that you kind of want the control plane that does all this logic outside the network. But when it comes down to Raft itself, there's the coordinator would manage who the leader is if the leader cannot communicate, and then all the nodes kind of transact along each other to basically pick a master. So if they send out, so if they can't, if say S4 stops, all these nodes, that least is going to time out because they can't communicate with S4, and then they basically send messages to each other, and then whoever is the first to basically send out that transaction then becomes the the master. I hope that answered your question, Haley.
Sure, technically not my question, right? But
Oh
yeah,
yeah, yeah. But yeah. So yes, it did ask a second question though, which is like if you have a multi-cluster setup, like how do you pick a master? So yeah, I'm just trying to find the point here where my charger is. Yes. So like if you have a multi-cluster setup, and usually like the reason why I went with the Apache and console explanation is that for this where there's just like a single network with only S4 coordinating, you kind of can get away with S4 kind of going bust, right? Because then, all these guys will be fine. Now, in much bigger networks with thousands of nodes, there will usually be partitions. And the reason for that is because network layouts, and I'm speaking like implementation detail here, networking the nodes gets more difficult the more nodes there are, because you can't have a single switch in the data center or the rack, like managing multiple nodes. Usually a rack, based on like the size, will hold like 34 servers or more, depending on like how big it is. So this could be like 34 nodes, but you have thousands. So you have like multiple switches, right? And you're basically transacting across each other using some overlay network like VLANs or something like that. So it becomes difficult because you can have network partitions like S4 and S5, S4 and S3 could be partitioned and they could just only be talking with each other, where S4 is the master. And then S5, S1, and S2 are then communicating with each other, where S5, S1, and S2 then pick a master amongst themselves, say S1, right? And this could happen amongst the racks. Someone could unplug a cable, right? And these things actually do happen in the implementation detail. So for multi-cluster, where you have, say, like those thousands of servers are like separated, right? Say 30 each, right? The way that it kind of work is that you would have a managed control plane on top of all the other masters. So the idea is that the master here, the master on the next node, on the next cluster setup, you can think of the cluster like the network here with 5 nodes or 30, depending on how you take the explanation. A new one there, a new one there, a new one there. And the idea is that all those masters manage their own network, and then they all reconcile on the shared control plane that then manages all the multiple masters, right? Or better yet, if you have multiple masters, you usually just run with Paxos. So, but then I don't think like that's the question you're asking. Just trying to be sure I answered that question correctly.
Yeah, no, totally. That makes sense to me. I think you answered both questions. So yes, that's awesome.
Yes, but then it's a very tricky question, because in Kubernetes we actually do have that kind of like multi-cluster setup, and the way they do it is that they don't go the route of multiple masters. They just have a shared control plane that then manages all the masters that run their own individual networks, if that kind of makes sense. But yeah, so like, but usually the Kubernetes case is kind of routing. So like if you wanted to reach, say like there's a resource here, the idea is that routing information for what master handles the control plane for this resource would basically just take the request on that like master control plane and then send it down to S4 that then manages this network where this resource is found. And that's basically how you reach it. So it's kind of like top level, goes down to S4, goes to S5, and if, it picks a master where the node is in there, then, it goes bust. But usually that's why you have a shared control plane managing, coordinating the information of all the masters, which is where, again, ZooKeeper or console comes in, because then this becomes what manages that consolidation process for your multi-master setup. But not multi-master, more like partition master setup, multi-cluster setup, as you described it.
So I wanted to ask, so for ZooKeeper and console, are they different protocols on their own, or they use the Raft to run what is it? Oh, Paxos.
I actually do not know. So the book even introduced me to, like, although this is just the atomic broadcast, I actually don't know what protocol ZooKeeper uses. I know ZooKeeper is just for coordination and managing configuration. So I don't really know. But usually ZooKeeper would, I actually don't know, to be honest. I don't know what consensus protocol they used. But I can just, but like, it could just be like a quick Google check, like ZooKeeper consensus algorithm, and it's Raft. So, no, it's not Raft. ZooKeeper is Zab broadcast, and then okay, it's just said ZooKeeper is a product, so it's kind of like Raft versus Zab, and it seems ZooKeeper is a broadcast protocol, but I don't see anything about consensus though.
I think you're like the layers of abstraction have been like kind of squashed together. So Zap would be on the same like level of abstraction with Raft, and I'm not sure Raft has like the base algorithm, right? Like the basic paper is something equivalent to ZooKeeper, because ZooKeeper is like another like protocol layered on top of like ZooKeeper atomic broadcast.
Yeah,
if that makes sense.
Yeah, but ZooKeeper would be, but the broadcast will manage state propagation. So it would kind of be how the messages get sent to each other, but not really how that state is then reconciled so that you can then arrive at consensus. So in a sense, like I get what you're driving at. It could just be like different parts of it. Like ZooKeeper might use Raft, or it might just have its own proprietary Zab is how the messages basically get sent. But then if it's atomic, then I guess that's kind of, it just sends it and then, you know, actually don't know, to be honest. I can only speculate so far, but I kind of see like where you're driving it, like it could just be like a different abstraction. But actually
I
don't
hope
know.
we're like too in the weeds. Did that answer the original question, Brian?
Yeah, it seems to, yeah, Zab seems to just be the consensus algorithm. See Zab.
Yeah. Okay, so Zab is ZooKeeper told me. Okay.
Yeah.
Yeah, it does.
Yeah, it seems they use broadcasts for the, what do you call it? For consensus. Zab. Data establishes synchronization. The data broadcast client updates. It just seems a bit like Raft, just now just for ZooKeeper, because it's the exact same process. Single leader does synchronization, data broadcast updates. That's one-to-one. So seems like the same thing. I don't know. Okay, no, but then it doesn't have a replication log. So that's kind of like the difference here with Zab. Like with the atomic broadcast, it doesn't need a, or maybe it does have its application. I don't know. Like you kind of have to read like the white paper and dive deep. So I'm only speculating here when I say all those things. So I actually don't know. Yeah. But thanks for the question. Very thought provoking. And thank you really for the breakdown there.
No problem. Does anyone have any other questions?
Okay, so yeah, if there are no questions, I guess we can call it a day then.